this. Okay, let's get started. So today we want to talk. First, we want to finish the factor graph part. It was interesting part. Let's finish that, and we are starting something new, but it's not really new. It's you already knew about that kind of, but we're gonna explain about that half a class. Hypothesis testing. That's something interesting to know about. So last class, of course, we talked about probabilistic models and graphical models for probability. We started with BaseNet and then factor graph, and we explained why factor graph is so important for us as like engineers or computer engineers or robotic engineers, whatever. Is very useful to use factor graph. We explained about how to define factors, what is the step to using factor graph. Today we're gonna build based off that foundation and talk about maximum posterior, how make the problem to a single consistent optimization problem and solve it in an efficient way using some methods like Gaussian Newton or Leeuwenberg marker method, and then move to hypothesis testing. So that's what we want to do. Let's get started. Just the simple recap about last class. We explained these factors. We said, okay, so how we define the problem as a factor graph? First, the problem need to be a stochastic for sure, need to have some posterior density that showing relationship between unknown and known. You have something wants to inference, you want to get inference that is unknown, and you have some known that are measurements. Okay, so you need to have this relationship. This relationship most of the time coming from posterior density, P of x given z. And this can be written as a prior and likelihood. And this is a Bayes, oh, my picture is there. Bayes rule, actually. So we knew like that. If you have a problem that can be break that up in these two parts, prior and likelihood, you can solve it with factor graph. That's you need to consider. And after that, the next part is to just defining x's or unknown variables that you want to optimize, and factors. For factors, last class we talked some factors are measurements factors, like for example distance to landmarkings can be a measurements. So in measurements, maybe before this class, when you were doing something like sensing in your robotic class or whatever, you didn't consider prediction. You just use sensor and measure the distance. That's it, and use that as a way to make decision. But in this class, we learned that no, it's not the proper way. Even though if you want to just use the sensing, if you want to just get z, if you just have a LiDAR, or if you have a sensor to give you the distance, you need to predict distance first and then compare that distance with this measurement to see how off is this measurements. This is the way that we are doing, and factor graph let you to do that automatically with defining factors. So when you have measurements, you have some predicted measurements that this prediction always have some noise, and this noise considered Gaussian most of the time for simplicity. And when you read measurements from sensor, you just need to find the likelihood of that measurement. See, this likelihood showing how good is this measurements, if it's off or if it's good enough, how we can check it based off this error. So if it's exponential family, exponent part is always error or residuals, because residual showing the difference between what you were predicting and what is the sensor telling. If this is close enough, is okay. If it's not, maybe this measurement is outlier. Maybe this is not a good measurement. Okay, so that's how the system works. So for each factor, we define the likelihood of that factor or the probability of that factor. It's not always likelihood, sometimes probability. Like for example, when you are transiting from one state to another state or prior, that's just a probability. And then find the cost or error. Okay, and this cost in exponential family factors is actually the exponent part. Why? Because when this exponent part gets smaller and smaller and smaller, so it means the costs get lower and lower and lower, the probability getting higher and higher and higher. Remember, this is how it works. If it's 0, when this is get smaller, the probability get higher. That's why. So that's why exponential family is lifesaver in so many cases, including here. Okay. So that was the measurement factor we already covered last class. I just do recap. And then prior factor. Prior factor is also important, especially in some tasks. You need to know, for example, you need to have or initiate some belief about your measurements. For example, the robot knows initial position and destination, and you want to find a path. You want to find a path between source and destination. You already know these two sources. You already know that the source is here. So you need to consider x0 or xn minus 1 very close to this. For example, was mu n minus 1. This was mu 0. This mu is a given values. You already know them. So that's a prior. So this x0 need to be close to m0, and xn minus 1 is also need to be very close. When I'm talking about very close, it means the covariance need to be very small. So this covariance need to be very small. And you can find the probability of that prior and also cost of that prior easily, because it's supposed to be very close to the close to the first point and last point. So this is very small. And using prior is important because prior is like anchor of the graph. It's kind of prevent global drifting, at least the first point is very important. Another factor that is in most of the project we are using, especially in robotic, is odometry or dynamic factor. Dynamic factor is between two states, between two random variables, two corresponding random variables, two consecutive poses, like x1 and x2, or xk and xk plus 1. So is important because kind of connecting all states together to make a trajectory. So you kind of connecting them together, and this factor is between them. This factor is connecting these together. So about motion model, when you are doing robotic, you already know the motion model. Motion model give you the next state based off previous state and input. So if you use some sensors like odometry sensors, odometry give you delta x, delta y, and delta theta, and that's u. U is the input. However, this has some noise too. So the relationship is also has a Gaussian noise. That Gaussian noise is part of them, especially when you have additive error. This noise is always Gaussian. And we can find probability of transition. So this probability of transition kind of forcing the trajectory to stay smooth, forcing trajectory to be smooth. So, and predicted, this is the predicted state, next state, and this is the next state, and these two need to be too close together. So, and the error can be computed based off that. So normally, odometry factor or dynamic factor, or sometimes we call it a smoothness factor, is bringing up the temporal space, is time, bringing the time involved. So, and make this temporal consistency is kind of propagating robot position in time and connect entire trajectory. So that's a very important factor. Most of applications, especially robotic, we have this factor, and this is different. It's not likelihood, it's also considered prior. Why prior? Because kind of give you some extra information to how move from one state to another one. Is it constant velocity? Is it constant, I don't know, angular velocity, you know? For example, if it's angular velocity, this transformation is not linear. And it's because it has sine and cosine inside. Okay, these three factors are they are using a lot. We for so many applications we use them. But if you have new factors, you also can make new factor. Like I made lots of factors for my papers. Like for example, consistency factor. I don't know, wind factor. You know, current factors, type of soil factor. I don't know, collision factor. What else? Obstacle avoidance factor. Like formation factor. You know, you have multiple robots, they need to get formation. They just need to get the factor. So you can make any factor you want based off your measurements that you have and the task that you are doing. Okay, anyway, you make lots of factors. You do them in a one single optimization problem. So that's the optimization problem that you're gonna make. You're gonna say that this state, unknown state, sometimes has landmarking or not. Landmarking is mostly for a SLAM problem. In a SLAM problem, you not just find your position, environment positions too. So in a SLAM problem, you have this. Anyway, if you have landmarking, that also consider part of the actually unknown variables that you need to estimate or predict. So this is coming from multiplication of all factors. If you have all factors, you just need to multiply them together and make one single consistent optimization problem. First is maximization, because you want to maximize these things, maximize this likelihood, but then become minimization after getting log. When you get minus log, it's get minimization, and log also eliminates some nonlinearity, like exponential families, or multiplication becomes summation. Anyway, the general and the final optimization problem becomes just sum of square errors. Sum of square errors. And sounds familiar, isn't it? Sum of square errors is well-known question. It still is non-linear, but is solvable in a very efficient way. One of the ways you can solve it using Gauss-Newton. Gauss-Newton I'm not going to go detail on Gauss-Newton, but normally using one actually linearize the function or this h, linearize this h function around actually the current estimate. The current estimate, we call it theta bar, and we are doing this linearization. So of course we can linearize that, and we can linearize that. We already saw this method of linearization using Jacobian. So because Jacobian normally the gradient showing the direction of that, so you have a function and around this theta you want to estimate that. So you want to find the estimate like the next step is from this step based off the gradient showing the direction of improving, so you can find the next step. So this is how it works. For each actually factor, we find this Jacobian and stack them all together. Like this is in one of my papers, actually is a new paper that I had for actually I think it was for unsignalized intersection problem when there is no signal for there and cars need to come and pass. So I consider some factors in that, and this is the A factor. So if you put A matrix, if you put all these Jacobians in a matrix form, you're gonna make this, and as you can see, this is a sparse. The other parts, they are not the white parts are all 0. The colorful parts are the values that already filled. Like for example, these boxes, orange or red, because it's x and y and x bar and y bar, it makes a 4x4. Jacobians become like that. This is for a start point, end point. This is all for actually odometry factors, but here I use Gaussian process. Another application of this, I use Gaussian process for a smoothness instead of having a motion model. I use Gaussian process as a motion model. The Gaussian process is also can be used for in this case. And also I use obstacle avoidance. This green one is obstacle avoidance. In this one is consistency between, I think that's, I consider consistency between the velocity of them. And this one is also something else, proximity safety. If two robots get too close together, need to. So as you can see, and this is another, this is B. B is just error matrix. So I just want to tell you that this, at the end, is gonna get A and B ready, and the rest is just computing is delta theta, and this delta theta in an iterative way can be just repeated. You are just repeating that every time the new theta is all the states. Remember, the old state is theta. And previous state, add with this delta theta that you already estimate that, gonna give you the new state. And repeat that multiple times to converge. That's how Gauss-Newton work. It's very simple, well-known method that can be used in this case. Anyway, this is some example in GTSAM. GTSAM is a library for Georgian Tech. SAM is a smoothness and mapping library, and they did very good job. And this is open source library. I already installed that in Windows, but in other operating system is much easier to install. I think for MATLAB also there is possibility to install it. I'm not sure about that, but it's very easy. So for example, this is a small SLAM problem. You define the graph. This is nonlinear factor graph. You define initial points. Then normally for factor graph, we initial for a state and then update it. So this is how it works. If you do that in a like time, that's also possible. Like for example, you want to update it in time. It becomes like a function of approximation, function optimization as well. You can optimize a function. Why it can be a function optimization? Because imagine you want to find the trajectory of a robot or path of the robot from one point to another point. There is obstacle, so that's a function and you are approximating this function. Anyway, you can use this, and Gaussian process also can be used the same way too. You know, they are very close because they are Bayesian. The relationship between them is this Bayesian assumption that we are doing a Bayesian and inference, you know. Anyway, we define that with initial, that we define actually landmarking, and we actually add prior factors, we add odometry factors, and we add actually all these measurements. We have 4 of these measurements reading to landmarking. We have 2 landmark, chair and table, for example. And then the rest is just calling optimizer. Here is, instead of Gaussian Newton, use Levenberg Marquardt. You also have Gaussian Newton too. This Levenberg is a little more advanced than that. And then you can find the result. Yeah, and the result is better than what you initiate. You know, you initiate with something, and then the result is better because you already, and this part is acting as a sensor to read distance to chair and table. Anyway, this is one example. Okay, so I think that's enough for Gaussian for factor graph. Let's have some new topic. It's not very new because you already use that for sure. Like for example, hypothesis testing. It's kind of like likelihood. You always test that. Like for gating, for example, probably you use that as well. So when you want to see, for example, these measurements belong to this target, or these measurements is outliers or is not, you're kind of doing this hypothesis testing, but you didn't know that this is called. Anyway, let's talk about hypothesis testing. So what is hypothesis testing? What is hypothesis? Hypothesis is something that still we are not sure. Hypothesis, when we are talking about hypothesis, it means you are doing that based on some data. You had some observations and you want to make decision based off observations, okay? You got some observations and you want to see these observations is okay or not. Something like that. So normally in hypothesis testing, we have some competing explanation about data. So for example, you observe some measurements and you want to determine is this measurements support or belief or not. Let's do example. Imagine you are tracking a target. So target is an airplane. Imagine this is an airplane. It's not look like airplane. Okay, so drone. You are tracking a drone using radar. Okay, you're tracking using radar, and in your radar screen, you get one measurements. You want to see is this measure? Can you assign these measurements to the target or not? Or maybe this measurements is outliers. You want to find that. So this kind of decision making, you consider 2 hypotheses. The first hypothesis is that yes, is it that belong to the target? So that's called null hypothesis. One hypothesis is that no, that's not a target. That's actually outliers. So that's called alternative hypothesis. So the null hypothesis is like default assumption, kind of, and alternative is a new claim, because we want to see if these measurements is belong to this drone or not. Like for example, there is a one measurement here. I don't know, it was something else, like something else or noise, whatever. You got something else and you want to see if this is because you need to do association. In tracking, you do data association. Data association means if you get some measurements, can you associate this to the target or not? Because that's gonna change the position of the target. Tracking is like that. So that's why it's important. But we already know that in these cases, we can do prediction. We can say, oh, the measurements supposed to be in this area. That's why I told you this course gives you lots of ideas. You did some prediction and find predicted measurements here because you knew this drone moving with this speed. So we find predicted measurements in this area, in this part. If this measurement that we found inside this, so it's okay. If it's outside, outlier. So this is how hypothesis testing can help us. So previously we knew if, for example, do Mahal distance. Mahal distance is good test for that. We can use that here too. That's why I said it's not very new. So in general, what we need to do for hypothesis testing, first we need to find hypothesis, H0 or H1. For example, here, the measurement is belong to target or not. Or for example, you do a SLAM problem and you want to see is it a loop closure happening or not. You need to check some features and say, oh, I saw already these features. This is familiar. But how much familiar? So you can say, okay, H0 is that the loop happened. H1, this is just false alarm. It's not really loop. Something like that. So we just need to check the possibility of these hypotheses that we have and check that. Sometimes, because that's why I'm saying we already knew about that. Sometimes we just did likelihood. Remember, we always say, okay, the likelihood of these measurements for H0 and likelihood of these measurements based off H1, we can compute these likelihoods, and these likelihoods coming from where? Again, Bayes rule and, you know, predicted. So we already compute them in a couple of slides before. For example, we computed the when you wanted to check if like a factors for measurements factor exactly the same. You know, we use likelihood of that measurements to actually is a good measurements or not, or likelihood or other things. Okay, anyway, so we can compute that, and so this is the first part. Find H1 and H0. H0 is a default one. H1 is our claim, the new claim. We are claiming that this measurement is not real. This is false alarm. Or this actually features that you read is not similar to what we saw before. This is a false alarm, something like that. The second part is to test it. But the test is like a statistic testing. So like what we did in finding these likelihoods, we computed a Mahal distance. Mahal distance is one of the test statistics that we are doing. Why is it statistics? Because in Mahal distance, you consider distance to actually distribution. Is not normal distance. It doesn't have unit. It's unitless. Like distance normally is centimeters, meters, kilometers, but in Mahal distance you don't have that. Why you don't have that? Because remember the Mahal distance was like when we say x like h of like h minus x Mahal distance sigma is equal to h minus x t transpose sigma invert h minus x. So this is Mahal distance. So as you can see that sigma makes the unique unit of, because this has the same unit, and when you divide it by that, the unit gonna go. So that's why this gonna be unitless. So that's the important part about Mahal distance, and this unitless gonna help us to do some distribution to find if this is good enough. So that's the main point of this hypothesis testing. The hypothesis testing, it wants to make this decision making more like mathematically makes sense. Like previously we say, okay, if the distance is 1 meter, is okay to consider it as a target. If it's more than 1 meter, is outlier. But what about if we don't have the meter at all? So that's why this hypothesis testing working fine in this kind of decision making. So that was the second part, test the statistics. After testing, we do decision rule. We compare the test with some threshold. So we consider some threshold when we check it. Most of the time for this threshold, we consider some distribution. Like for example, in actually Mahal distance, because Mahal distance is a square, there is chi actually distribution that we're going to talk about that. With chi the square distribution, you don't need to have that. You easily can find this threshold. You don't need to be worried about that. I'm going to talk about that. After finding that, you also can see how confident are you. You can even check how confident you are. However, this confidence is related to, these two are very related. So if you want to make decision rule, you also need to consider confidence. You go, okay, I want to have like 95% confidence. Most of the time, 95 is something that we use. Most of the things, most of decision making is 95% is enough. 95% accuracy is enough. Okay, let's go for 95. Let's do example to see how it works. So this is for target tracking. We have a measurements, and we already have predicted measurements. When we put this in top, means it's predicted. We predicted this. So when I'm talking about prediction, it means my model tell me that measurements is here, but we still don't know measurements. We still need to measure it. So this is predicted measurements, but predicted measurements is has covariance, and this is the covariance of that. We have covariance of predicted measurement and predicted measurement, and then we use sensor to read the real measurements, and this is the real measurements. Okay, now we need to find Mahal distance. Okay, what is the hypothesis? The hypothesis that we have, we are saying, okay, these measurements is belong to target or not. If it's belong to target, it means it need to be close to predicted measurements. Close enough. How much? Threshold. How computed? Chi-square. Okay, let's do it. First, let's do actually hypothesis that we have. So this H0, if H0 be correct, means what? If H0 is a default one. Default one is that the new observation is belong to target. So if it's belong to target, it means it need to be in this, it need to be around Z bar with this covariance. It need to be inside this. But how we can prove it? With using Mahal distance or Mahalanobis distance. Mahalanobis distance doing amazing testing for us. A statistic testing, you know. We do Mahal distance, and when do Mahal distance, we find D square. D square is 5. Is it 5 meters? No. If it's 5 centimeters? No. Kilometers? No. Doesn't have unit. Interesting. Doesn't have unit, but it has something. What is that? It has something on it. And that's something interesting. So let's see what is that. So this Z and Z hat, is it hat? Anyway, hat, they are both Gaussian. Is the distribution of D2 is also Gaussian? No. If you square actually sum of some square, if you add them together, this gonna make a new distribution called a chi-square. So that's chi-square coming from here. So chi-square is actually depend on degree of freedom as well. If it's like 2 degree of freedom, like for example in 2D dimension, x and y, you put a 2 here. In 3, you have different values. Like for example, this picture is very small. I can make it bigger with this, I think. Oh. Yeah. So in this picture, as you can see, this red one is for 2 degrees of freedom, and the blue one is for 6 degrees of freedom. As you can see, in 6 degree of freedom is still like a bell shape, but it has a big tail. So is skewed, is not symmetric like normal distribution, because it's a square of normal distribution. So, but we are in K2, so so this yellow one is correct. So that's what we want to test. So this is how we can find the threshold. For threshold, we need to know confidence level. Confidence level showing how confident you are. You have some a significance level that coming from this alpha, and you just need to, this alpha, if n is 0.05, the confidence level is 0.95%. So this is most of the time, as far as I use this a lot in multi-target tracking, in estimation, in approximation, it's in prediction. I use that a lot in so many algorithms, especially tracking, and always I use 95% confidence. If you use 95% confidence, this actually threshold gonna be 599. And always was 599. From that time, I didn't use the rest of computing. I just used 599. And if the Mahal distance give you about 5 to 599 is okay. You can consider that as a target. So that's something that we always need to consider. If this D is smaller than 599, you consider H0. Other than that, H1. You reject H0 in other way. So this is how we do decision making in a stochastic way. The chi-square, if I talk a little bit more about it, so chi-square is actually, if you multiply, first of all, why this is called chi-square? Because this alphabet called chi in Greek, but the person that introduced that the first time was Pearson in, I think, 1900, that time. However, later, another method that we're going to talk about that right now as well is called a likelihood ratio is another way to test that. In addition to chi-square, we also can use likelihood ratio. Likelihood ratio we already knew. We compute the likelihood of belonging to the measurement to the target and likelihood of not belonging, and divide them together and see if this is big enough, consider that or not. That's another way. So you have normally two ways for decision making. One is like using chi-square, and the other one is likelihood ratio. Why is ratio? Because we want to make it unitless. Anyway, that's a chi-square. So chi-square is always positive, unitless, and skewed, as you can see. And you can find and it's based off degree of freedom. So for example, chi-square, it depends of degree of freedom and confidence level, and confidence level too. Okay, so the last part that we want to cover is a likelihood ratio. Likelihood ratio, we already know. We compute the likelihood of measurements belong to hypothesis 1, that is what we are claiming, compared to the null hypothesis. We compare that and then check it with a threshold. If it's bigger than that, we accept, for example, H1. If it's less than that, we don't accept it. So something like that. So this is something simple that probably we used that a lot before as well in other projects. So let's do example. In this example is a loop closure that I already talked many times in this class. When you want to see in a SLAM problem if a loop closure happening or not, normally you are checking if you've seen already something before, and you need to check a match, if there is a match between whatever you saw before or not. So you have already, you can say you have two hypotheses. The first hypothesis is the match is false. The match is false, and appearance is accident. Is not actually loop closure. And the second one is that it is loop closure, that loop closure is true. So we need to find the likelihood of them, likelihood of H1 and H2, and divide those together. And if this value is bigger than one threshold, so we can reject it or accept it, something like that. So that's it. I think this was whatever I could tell you in this semester, and today is the last class. So I hope it was useful, and we covered lots of the concept. Actually, we did lots of theory, I think, problem solving strategy, and in real world applications. And I think I wanted to help you understand these methods, how they work, and how we can use them in practical applications. And thank you so much for being good in the class, attending a class. Even last class, you all came here, even though this is not part of your score, and your score is already probably done with your project and stuff. But thank you so much. But still.